So this lecture will be finishing up our discussion on electrochemistry and detailing how the reduction potential and the cell potential relate to the thermodynamic concept of delta G and the equilibrium concept of the equilibrium constant K, how all those things are related. And then we'll be, the second half of the lecture will be kind of a brief discussion on metallurgy, how metals are isolated from their mined minerals, and then how those metals are combined with other metals in the form of alloys to make useful materials. Okay, so this is coming from section 4 of chapter 21 and chapter 22, section 3. First, let's try a review question. Consider the following half reactions and select the strongest oxidizing agent present. Right, so remember what an oxidizing agent is. It's something that gets reduced. So we're, in a sense, trying to pick the thing that is best at getting reduced. And these are all reduction potentials, which measure the potential of these things to be reduced. So if we look at our choices, how easily each of these will get reduced, right? The highest reduction potential we have here would be negative 0.28. So out of the three choices we have here, the top three here, we could select C, be the has the highest reduction potential, and therefore it's the strongest oxidizing agent present. Okay. So for a spontaneous reaction, we know that delta G has to be negative. We know that the cell potential has to be positive. There's an equation that relates the two together, and that's here. Delta G equals minus N times F times the cell potential. N is the number of moles of electrons that are being transferred. So in your equation, if you have 2 electrons that are being given up by your metal that are being transferred in your cell, the N value would be 2, and so forth. So, and F is actually a constant. That's Faraday's constant, and that's this value here with these units. Okay. And we can write this under standard condition, just put those knots in. Okay. We can also relate this to the equilibrium constant. Right? If we plugged in the equilibrium, the expression for equilibrium constant with respect to delta G, what we'd get is RT ln of K over N sub F if we solved for cell potential, right? So we'd have to be multiplying or dividing by negative N sub F, negative NF, excuse me. Okay. So those two equations will help us. Okay, and the delta G, how delta G relates to K, that's just negative RT ln of K, right? And so if we combine these two equations, we get this one. So you can now interconvert delta G, K, and cell potential with these three equations, right? And what conditions are met at when something is spontaneous? Delta G is negative, K has to be greater than 1, and the electrochemical cell is a positive value, that potential for it. At equilibrium, delta G and cell potential are both 0, K is 1, and then non-spontaneous reactions will have a positive delta G and a negative cell potential, and a K value under 1. Okay. The Nernst equation relates the standard cell potential to a cell potential at any given moment. And what changes? Well, the concentrations of your components in the cell might change. They might be something other than standard state conditions, which would be 1 molar concentrations for everything. So that's where we get this Nernst equation. Okay? And K becomes Q when it's not at equilibrium. All right, and remember, when Q is less than 1, that means Q and K are solved by the products over the reactants. So if Q is smaller than 1, that means the reactant concentrations are greater than product concentrations. Right, so if that is, the ln of that is less than 0, negative, that means the cell potential is greater than the standard cell potential, right? Because if this term is negative, that's going to be a negative of a negative. You're going to add it to the standard cell potential, so you're getting bigger from there. When Q equals 1, reactants equal products, Q is ln of Q is 0, then ln of 1 would be 0. So if their reactants and product concentrations equal, this term cancels out, so the cell potential equals the standard cell potential. Right? And when Q is bigger than 1, that means reactants are less than products. That means ln of Q will be a positive value, greater than 0. So this term will be negative still. So the cell potential, standard cell potential, minus this term, you're going to be less, your cell potential will be less than the standard cell potential. Right. You're going to simplify this equation as before. If T is at room temperature 298, it simplifies to this. So that might be a good equation to remember for homework. So let's try a practice question here using the Nernst equation. So in a test of a new reference electrode, a chemist constructs a voltaic cell consisting of zinc 2 plus half cell, and an H2 H plus half cell under the following conditions. So zinc 2 plus is at 0.1 molar concentration, H plus is at 2.5 molar concentration. We have a pressure of 0.3 atmospheres for the H2, right? And then we're calculating the potential, the cell potential at 298.15 Kelvin. Right, so for this, we have to first calculate a Q value. And Q, remember, is going to be products over reactants. So our products in this case would be H2 gas and zinc 2 plus. And reactants, we have zinc solid metal, but that doesn't factor in to an expression for Q or K because the solid isn't changing in concentration, right? It's a solid, so we're only dependent on H plus. But there's a 2 out here in that balanced equation, so we have to make that concentration squared. Okay, we can then plug in our values. We use the partial pressure we're given for H2 as atmospheres, and then concentration of zinc 2 plus was 0.01, and then we have 2.5 molar H plus. We square that value, and what we get is 4.8 times 10 to the minus 4th. Okay, so that's something that we could plug in. Our standard cell potential is another thing that we can calculate using our standard reduction potentials. So that's just going to be our anode minus our cathode. So plus 7.6 volts, right? The anode, cathode minus anode is how that's calculated. So our cathode is going to be the one with the highest reduction potential, which in this case would be hydrogen. And now we can calculate our cell potential at the concentrations given. It's just going to be our standard cell potential. Remember, those are all at 1 molar concentrations. And so this, now we need to determine, okay, what is our N value? So our N value is going to be, in this reaction, we're transferring 2 electrons, so N equals 2. So we can just plug in 2 for that. And then for Q, let's plug in what Q is, 0.76 volts. And then for electrochemical cell, let me just erase that. Try to save some space here and actually plug things in. So this is 0.76 volts, and this was Q 4.8 times 10 to the minus 4. Okay, and so when you do that and go through the math, the cell potential at these conditions is 0.86 volts. So higher than the standard cell potential. So these concentrations are more advantageous. Okay, next problem we will consider this electrochemical cell that's given with the anode of zinc to zinc 2 plus and the cathode of bromine to bromide ion. We have another thing listed here, platinum. This is a case where we're just using a different material for the electrode because bromine 2 is a liquid and the bromide is an aqueous solution, so neither of those can really act as the solid electrode, so we have to use something with that, and that's platinum. Okay, so first, use the data below to calculate the standard potential of this cell, or the cell potential, right? And remember, the cell potential equals the reduction potential of the cathode minus the reduction potential of the anode. Okay, and so in this case, what's the cathode? The cathode is going to be the one that's higher value for reduction potential, so that would be bromine. So that's the cathode minus the anode, which is zinc minus 0.76, right? So the cell potential here is 1.83. Is this reaction spontaneous? Well, yes. I'm going to wait to draw it to the end, but answer these next questions first. Cell potential is greater than 0, so it's spontaneous. What is the value for delta G in kilojoules per mole? And it gives us a value for F here. Remember, that relationship is the cell potential equals minus NF, should be delta G equals minus NF times cell potential. So we can just plug in minus N, so N is 2, we're transferring 2 electrons here, F 96 kilojoules per mole times volts, and then the cell potential is 1.83 volts. So delta G in this case is equal to negative 351. So again, it's a negative value, and that's in kilojoules, so it is spontaneous. Okay. And the last thing, draw the cell. Okay, so let me erase some of this. I will draw it up here in this little space. Erase that. Okay, so how would we draw this? We would draw just basically for the anode first, we would have zinc 2+ in solution and zinc metal. Okay, and that would be connected to our cathode, which has a platinum electrode. And in solution here we have bromine going to the bromide at that electrode. Okay, and then a salt bridge, and I forget what they don't really tell us what's in there, right? But negative charges would be moving towards the anode, and positive charges would be moving towards the cathode. Okay, and our electrons would be flowing in this direction, from anode to cathode. Okay, so we have our relationships between the cell potential and the log of Q for this zinc copper cell that's shown below. If Q is less than 1, right, remember what that means. That means that the products are lower in concentration than reactants. So if it's less than 1, Q is less than 1, products are lower in concentration than reactants. Okay, and so that's in this region up here. The potential of the cell is greater than the standard reduction potential. That means the cell can do more work. Right? If Q is greater than 1, that means products are in greater concentration than reactants. Right? And that means ultimately your potential at that particular stage is less than the standard cell potential, so your cell can do less work than at the standard conditions. There's something called a concentration cell, and these exploit the effect of concentration changes on cell potential. The cell has the same half reaction in both cell compartments, but with different concentrations of the electrolyte. So in this case, if you have copper and you have in solution with a small 0.1 molar concentration of copper 2+, and then in the other cell you have 1 molar concentration of copper. If you use the low concentration as the anode and the high concentration as the cathode, what you get is a net movement of electrons from the higher concentration to the lower concentration. As long as the concentrations of the solutions are different, the cell potential is going to be greater than 0, and it can do work, right? And the cell potential is based on the differences in these concentrations. So that would be shown in this figure, right? A darker blue solution here at the cathode, right? So we're going to get electron. There's a force, electromotive force to get electrons from here, from this side, in the solid, right? Giving up electrons to go into solution to reduce copper 2 ions in this side. So you're going to be losing solution in this chamber and gaining concentration in this chamber, and until they equalize. Once they equalize, there's no more motive of force to drive electrons, so that's when this cell would stop. The last thing we'll sort of talk about here with electrochemistry are some biological applications to it. And one example is in mitochondria. We have in the intermembrane space, we have a proton gradient being generated. Okay? And that that gradient that's generated, protons are being pumped from the matrix of the mitochondria into the intermembrane space. And those proton gradient sets up an electrochemical gradient, which is then used to produce ATP, just in very brief terms. Okay, so that's one of the reasons, that's how the cells make ATP. Okay, how they generate this proton gradient is by transferring electrons. And they have the electron transport chain with different complexes, 4 different complexes. So from, usually anything you eat for aerobic organisms ultimately are going to generate electrons that can be passed through the main respiratory chain, as it's called. And those transfer of electrons is what drives these protons to be pumped. And then ultimately those protons are used to generate ATP, which is used to power processes inside the cell. Right. Well, here's one aspect of metabolism that I've studied, fatty acid beta oxidation, so breaking down of fatty acids. The first step of this involves what are known as acyl-CoA dehydrogenases, so enzymes that catalyze that first step. Electrons generated from this step are incorporated into the FAD molecule, and it becomes FAD2 when it's reduced, FADH2 when it's reduced. These dehydrogenases then transfer electrons to the FAD group on a protein known as electron transfer flavoprotein, or ETF, and then ETF transfers them to ETFQO, which then transfers them to a molecule called ubiquinone, or Q. Also coenzyme Q10 is another name for it, which you might have heard of. That transfers electrons to then complex 3, then to cytochrome C to complex 4, and then complex 4 ultimately gives them to oxygen, O2, to form H2O. And that's why we breathe in oxygen, is to be an ultimate electron acceptor in this chain. Right? The problem with these two proteins, and this is something that really is just like mentioned in a sentence in a biochemistry book, not really talked about in detail, these two proteins, this step connecting fatty acid oxidation to the main respiratory chain. But if you have problems in these via mutations, either of these two proteins, it leads to a disease called glutaric acidemia type 2, which is very, very severe. So even though they're not mentioned very much in a biochemistry text, the absence of them, or even if they're not working at full capacity, it can lead to a very severe death, disease and death. Okay. I've studied ETFQO a little bit in some detail, and it has 2 cofactors, an FAD and an iron-sulfur cluster. Right? And the iron-sulfur, both of them can be reduced. The iron-sulfur cluster can gain 1 electron and go from a 2+ state to a +1 state. And the FAD can gain an electron to go to FAD-. It can actually gain 2 electrons to go to FADH2 as well. Okay. When you add mutations in the structure around the iron-sulfur cluster, to amino acids that are 8 hydrogen bonding to it, you can remove some stabilizing interactions, and you see that when we look at the reduction potential of the wild type enzyme or some that have mutations by the iron sulfur cluster, you see that the reduction potential gets lowered, right? So what does that mean? It means it's harder to get and add an electron to that when it is mutated. Right? And we can do that as well to the FAD. The FAD have two steps though, a first electron and a second electron. Okay, but when we just take that midpoint there of the two, when we add mutations, the wild type version of the enzyme is higher, and we have lowered it. We've made it harder for that cofactor to accept electrons. Right? The other important aspect of this is, the iron sulfur cluster has a plus 37 reduction potential. The FAD had a plus 47. So this kind of proved the electron movement through this enzyme goes into the iron sulfur cluster first, then into the FAD cofactor. Okay, so that was just a little aside about some work that I have done involving redox chemistry. Okay, moving on to metallurgy. We won't spend a whole lot of time on this in this class, but I think it's interesting, and so many things around us are made from metals that it's good to have an idea of how they are made industrially. So metallurgy is the technology of metals and is concerned with their extraction and utilization. Pyrometallurgy means that heat is used to obtain the metal. Electrometallurgy employs electrochemical or electrochemical steps. And hydrometallurgy relies on aqueous solution chemistry. So all three things that we've sort of talked about in this class. Extraction of pure element from its ore involves a series of steps, beginning with first obtaining that ore via mining. The mineral contains the element, while the what's known as the gagnu is the portion of the ore with no commercial value. All right, so here's some common mineral sources of elements. Not important to know these in this class, but if you're interested, here's some of them. Probably the most applicable to our class, I would say, is maybe limestone. That's where calcium comes from, so industrial calcium. Iron, that ore is called hematite. All right, here are the basic steps of metallurgy. First, you have to mine it. Right? You have to get an ore. Then there's a pre-treating of the ore, either magnetic attraction, something called a cyclone separator, which we'll see a picture of, flotation, leaching, some sort of pre-treating. Then you're converting the mineral to a compound. So in the pre-treating, you're kind of separating the mineral out that you're interested in. Then you convert it to a compound. And that's, via roasting. That's pyrometallurgy or hydrometallurgy. You then take it to the next step, another converting step. So you take the compound into a metal. And this is via things like chemical redox or even electrochemical reactions. And then once you have the metal, you can refine it. There's some different refining methods here. Distillation is one that you might be familiar with, although maybe not so much familiar that it can be used to refine metals, as well as we usually think of that as sort of like a volatile chemicals like gas or something like that, but it can also be used in some cases with low boiling point metals. Right? And then finally, alloying, that's the mixing of metals together to form a compound that has specific properties that you're looking for. Okay, so we won't really talk about the mining, the first step. That's really outside of the scope of this class. But once you have an ore, how do you treat it? So this is the second step. So magnetic attraction can be used to separate magnetic minerals from what's known as the gagnu, the unusable part of the ore. Density separation can exploit large differences in densities. And an example of that would be when you're panning for gold. You're relying on the density differences between gold and sand. Right? Flotation uses an oil detergent mixture to form a slurry, which is then mixed rapidly with air to give an oily, mineral-rich froth that floats. And leaching involves the formation of a complex ion that is water-soluble. Right? So in leaching, we've talked about complex ions in the class, so here's an industrial use of them in leaching when you're pre-treating an ore. Right? We mentioned the cyclone separator. Here's a figure of that. So you have this pulverized ore that goes into it, and it sort of spins around here, and you have lighter particles that you're not really concerned with. This is using a difference in density as the method of separation. So your heavier ore will kind of spin down and go towards the bottom. I should say the mineral, right? The ore is what we're trying to pull the mineral out of the ore. So heavier mineral will go down, and the lighter particles that you're not interested in the ore will go out up at the top. The flotation process, which was mentioned here, you have the ore oil detergent mixture. It goes in. You're mixing it here with air bubbles to create a froth. And so the gagnu, which is kind of just like rock or sand, kind of stays at the bottom, and that oily detergent mixture with your mineral goes to the top. Right. The next step is to convert your minerals to compounds. And one way to do that is to make them, the metals, into their oxides, because oxides can be reduced easily. So in this case, if you have like calcium carbonate, that's our mineral from limestone, we would heat it up, and that makes calcium oxide and carbon dioxide. Right? The carbon dioxide goes off as a gas, and the calcium oxide is what's left. Metal sulfides are also converted to oxides by roasting in air. So like something like zinc sulfide, if you roast it in air, it makes zinc oxide and SO2. Next is a conversion of your compound by some technique. In this, we're going to look at chemical redox. So if we have our oxide, in this case a zinc oxide, you can combine that with carbon, and you get this redox reaction where now you have a zinc, I think that should say solid, not gas, and carbon monoxide. So you've transferred that oxygen to carbon. Oxides that are less active metals can be reduced with hydrogen instead of carbon. So in this case, tungsten oxide with hydrogen goes to tungsten metal plus water. More active metal may be used as a reducing agent as well, so you can get kind of like a displacement reaction. So in this case, chromium oxide mixed with aluminum, you'll get chromium plus aluminum oxide. Right, thermite reaction is an example of this. You might have heard of thermite. It's an aluminum powder. It's used to reduce metal oxide it has a very exothermic reaction, and then it produces a molten metal. So in this case, this would be the example of the thermite reaction, right? And the metal we're producing, chromium, is actually not even a solid. It's a liquid, because this is such an exothermic reaction. You can also use a electrolytic cell. So something like this liquid beryllium chloride can be used, and you undergo reduction at a cathode, right? So if this is your liquid in the cathode chamber, you undergo reduction to solid beryllium metal. Okay. This periodic table kind of shows you redox steps in converting a mineral to an element. Right? And the ones I just wanted to point out, these sort of common metals, right? Iron, cobalt, nickel, copper, silver, zinc. In gray, these are the ones that you reduce that oxide with carbon, either in the form of what's called coke or charcoal. Right, so that's a very common method. Okay. So the next step's refining and alloying the element. Refining, that's another fancy way to just say of purifying it. That's carried out by one of the following three methods: either electrorefining, that employs an electrolytic cell in which an impure metal acts as the anode, and the pure metal as a cathode. So the impure metal is it's at the anode, and the pure metal is at the cathode. Distillation is used to refine metals with low boiling points, as I've mentioned before. That's a possibility. And then something known as zone refining, that exploits freezing point depression. We don't really give any examples of that in this class. Okay. Many metals are used as alloys rather than their pure form, and that's because some metals in their pure form just aren't strong enough or aren't resisted to corrosion at all, or enough to be used in structures or in things that would be outside, exposed to elements. So what's known as alloying, or combining them with other metals in different proportions, that's used to produce the material that has the desired physical properties. So one example of zone refining, which I said there wasn't examples of, but this would be an example of zone refining. You pull impure silicon now is pulling through a heating coil. So in that general area of the heating coil, you get molten silicon, and you're pulling through this very slowly. And as you pull it through, the impurities that are in that silicon rod kind of stay in that molten region, and then the solid silicon that comes through the other side is pure. Right, here are some important alloys listed. Don't need to know these or their compositions for this class. Understanding what an alloy is sufficient and why alloys are made. Stainless steel is one that you've probably heard of. It is actually iron mostly, but it has some chromium and some nickel in it. Okay. So that's one that's fairly important to us in daily lives. Bronze, right? You might have heard of the Bronze Age, and so that's what really led to the first big advance in technology. Is this concept of being able to make an alloy, mixing metals together to get something that's stronger, more resistant to corrosion, and thus you could make a lot better weapons out of it, and better building materials and better tools. And so that's really was a huge jump forward in civilization. Okay? And so bronze was, mostly copper. Then that's what people had been using before. But copper is a pretty soft metal, and that people found that when you add zinc and tin to it, you can make it much stronger. Okay. Sterling silver, if you're interested, is mostly silver, but it has some copper in it. And then the 14 karat gold, 18 karat gold, that jewelry gold, is gold, but also has silver and copper mixed into it in different proportions. Here are 3 binary alloys. Vanadium carbide is vanadium and carbon. Brass is copper and zinc. And then this Cu3Au is copper and gold. And that just gives you an idea that alloys will take up different organization patterns, unit cells that we've discussed in solid state chemistry. So aluminum and alloys made out of aluminum are obviously very important in modern society. Many things are made out of aluminum. The one step in the production of aluminum is this electrolytic cell, and the components of it has graphite anodes and a graphite furnace lining, and so these are interacting with this molten aluminum oxide dissolved in sodium aluminum fluoride. So very kind of complex mixture there. But what's happening is that you're getting a reduction of the aluminum at that cathode, that lining of the surface here, and it's reducing to aluminum metal, right? And then that molten aluminum metal can then flow out of the chamber. Right? And as mentioned, it's very important, and here's just some uses of it. Lots of parts on cars and trucks are made out of that, aircraft, so transportation is a big deal, consumer durables, building stuff, packaging like aluminum cans or aluminum foil, machinery. So there's many uses of it, and one reason why is that it's a very active metal, so it doesn't really corrode. It will oxidize and form aluminum Al2O3 on the surface of the metal, but that adheres to the surface, and it keeps the oxygen from penetrating lower, so it doesn't really as we think of like iron rusting out. It stays all on that surface as a protective layer. And so that's why aluminum is such a good material, and it's used in many, many different alloys. All right, so that is all we have for metallurgy. Next time we will begin a 4-lecture series of a survey of the periodic table.